So hello guys, in this video we'll be talking about Thiessen Polygon. So we were talking about neighborhood analysis in the sub part of spatial analysis chapter. So we looked at overlay analysis in the previous video, and the video that was immediately before this video we looked at buffer analysis. So buffer analysis, and we had also discussed that in neighborhood analysis and in proximity analysis, two of the most important analysis that we do in GIS are buffer zone generation and Thiessen polygon generation. So in the previous video we looked at buffer zone generation, and I showed you videos and I showed you examples on how buffer is used for different analysis. And in this video, we'll be talking about Thiessen polygon generation and Thiessen, what is the meaning and what is the use of Thiessen polygon. So as we all know that there's a geography law that is known as the Tobler's first law of geography, which says that everything is related to everything else, but near things are more related than distant things. So in this universe, everything is related to everything. But the things that are near to each other are more related to the things that are distant from each other. For example, if I live in Pulchok, the people who live in Kupandol might have a similar lifestyle to the people of Pulchok than the people who are living in Banisur, for example, right? Because since Kupandol and Pulchok are quite near, so the lifestyle that we have might match. So this is some kind of patterns. We see some kind of patterns and characteristics all around the globe, and like Tobler has just seen that, and then he just made it a quote. So it is this principle is fundamental GIS and spatial analysis, emphasizing that spatial proximity often implies similarity in data, patterns, and relationships. It forms the basis for spatial autocorrelation and many GIS techniques. Okay. So why am I saying this first law of geography again then? So it is very much significant when we are talking about Thiessen polygon. So what is Thiessen polygon then? I'll show you by one example. So what you can see is, so Thiessen polygon is some kind of polygon that is formed. For example, in this picture, let me give you an example, okay? So this P1, P2, P3, P4, P5 are rainfall stations. Here, these are rainfall stations. And as you know that it is not feasible and it is not economical to keep rainfall stations in all the places. So what usually hydrologists or what usually government officials do is they have rainfall stations at particular locations. They do keep it at a certain interval, and what they assume is this area, for example this P3 has 50 millimeter rainfall that day. So what they assume is this place, all the places that are inside this polygon, they too have 50 millimeter rainfall that day. And what is the basis of that? Because these areas are near this P3 station. And whereas this P1 station, this area A1, since this area is near to the station P1, what it assumes is that all the places that is near this, inside this A1 area, has faced similar rainfall as of P1. Right? So in this way, polygons are formed, and these are Thiessen polygons. So what is the spatial characteristics of such polygons is that what you can see here is, for example, this point. We have a point here. So let me show you by one example. So what I would do is I would take a screenshot of it and I would bring it to MS Paint, for instance. So we have a picture here. So let me draw something. So this point, let me do it in yellow. No, green. So we have one point here. So if you look at this point, the point that is nearest to this area, the nearest point in P1, P2, P3, P4, P5 from this green point is P2, right? If I go here, it's still P2. But what if I go here? In this case, the nearest among P2 and P3 is the nearest point from this green. So just by these computations that take place internally, Thiessen polygons are formed. So every area, every point that is within this area, for example this point, this point, this point, this point, the nearest station from these points is P3. That's why it has an area bound to it. So this is the area where all the characteristics of this area is similar to the characteristics of P3. So this is how the Tobler's first law of geography is related in this station, right? So this is just one theory. So like if you look here now, so in this we have used geometric distance for determining neighborhoods. So basically we have created neighborhood polygons that are near that stations, near that points. So what does this technique do is this technique will generate a polygon around each target location. So in that case there was rainfall stations that identifies all those locations that belong to that target. So that belong or that have similar characteristics to that target. So let's learn how we can create Thiessen polygons in QGIS then. First, let me make a polygon. So I'll create a polygon which name is catchment. Okay, so it'll be a shapefile. Let me do it on the projected coordinate system. Okay, so since we'll be doing some computations afterwards in meters or square kilometers, let me do it on projected coordinate system. So the geometry type would be a polygon. So integer 10. Okay, so I'll add a field which name could be area, or so let it be. So this is 1. Okay, so let me do some editing and create a polygon. Okay, so I have a catchment of this kind. So the name of the catchment is 1. Let me save it. Let me create rainfall stations now. So these are just hypothetical cases. Okay, in actual you will receive data of it. So let me create rainfall stations. And let me create a shapefile. Okay, then what it'll be points, and then it'll be in projected coordinate system as well. Okay, so I'll create rainfall stations now. So the rainfall station 1 would be here, it'll be 1, another would be here, it'll be 2, different will be here, it'll be 3, we'll have here, it'll be 4, we'll have here, it'll be 5, we'll have here as well, it'll be 6, here 7, 8. Is this enough? Maybe. Let me create one here. It'll be 9. So okay, so I have 9 rainfall stations here. For ease of seeing, what I would do is I would just change the symbology. So let me do it to apply. Okay, so these are red are my rainfall stations, and this is my catchment, for example. Okay, so now here you'll see so here is one feature called Voronoi polygons. If you go here, if you have rainfall stations here, so now let us create okay, so rainfall stations here, input layer is rainfall stations. Okay, now I create Voronoi polygons to run. Close. So just give me a minute. So now I'll be creating Voronoi polygons. Okay, so what I would go is I would go here. So here's in geoprocessing, in analysis tools, or in research tools. Here I have Voronoi polygons. So what I would do is I would create with the help of in rainfall stations, I would be creating Voronoi polygons. Run. So I've created polygons, right? But now I would want to see, I do have polygons here. I can change its features to make it more visible. So I'll just symbology, I would not be doing simple fill. It'll just be solid, stroke color, it'll just be a transparent fill. Okay, so apply. Okay, so now you can see which rainfall station will have which area coverage, right? So for example, this point might be closest to this rainfall station rather than this rainfall station. So that's why this area, we can use rainfall data of this rainfall station. But what you can see is these areas are just left blank, right? So what we can do is, in such case, we can create another Voronoi polygon. Let's delete this. We'll increase the coverage. So we might increase the coverage to 15 or 10. It's a hit and try. So what I would do is I would create a different Voronoi polygon. It's Voronoi, and then here you have a percentage. I'll do 10%. Maybe it might cover up. No, okay, I haven't set up the. So run. Now you can see that almost all of my area has been covered. So now what I can do is I can delete this one. I will remove layer. Okay, so I'll change this properties as well. I'll remove the color, so transparent fill, and this will be solid. I'll change its color to maybe dark orange. Apply. Okay, so now you can see which areas have been covered. Okay, so now what I want to do is I don't need these other areas, right? I just want the area of the catchment where I can use the data of that rainfall station. So what I can do is, as we had learned in overlay analysis, I can do intersection. So my input layer will be the catchment, and my overlaying layer would be this polygon. Since in this Voronoi polygons, if you look at the attribute table, it will have the number of polygons. That number of polygons will be equal to the number of rainfall stations here. So here, if you look, the number of rainfall stations, it is 1, 2, 3, 4, 5, 6, 7, 8, 10 rainfall stations. So that's why we have 10 different polygons. Okay, so what we can do is now we can go and do intersection, where my input layer would be the catchment for sure, and the overlaying layer would be the Voronoi polygon, and then I would run it. So now I have, if I don't need this, I don't need this. Okay, so I already have the catchment has already been demarcated as per my rainfall stations. So if you look at the rainfall stations, so now what this means is this is the boundary of my catchment, and these are the polygons, the areas where I can use the rainfall data. So for example, if I show labels, then in this area I can use the rainfall data of 5. In this area I can use the rainfall data of 5. In this area I'll use the rainfall data of 1. So that is the meaning of Thiessen polygon, right? So now I want to compute the area, right? So if you look at the intersection, what you can see is, if you look at the attribute table, we just have the ID number, right? We just have the ID number of the ID 111, and we have the ID number of the stations. But what I need now is I need the area of it. So what I would do here is I would do okay, open fill calculator. So what I can do is I will compute the area. So output full name would be area in square kilometer. So what I can do is I can compute the area. So the area, right? And what I'll do is I'll divide it by 10. Since we'll be getting in meters, square meters, right? I would just need it in square kilometers. So what I can do is okay, so this much will be enough, I guess. So I'll have a different field it'll be a decimal number. Okay, so now I have a different field in which I have area of square kilometer, this of every polygon. And if I want to see how much percentage it covers of the total catchment, what I can do is I do have the polygon of the total catchment, right? So I'll turn it off right now. I do have the area. So what I can do is I can compute the area of the catchment in the similar fashion. What I would do is, since this is the attribute table of the catchment alone, I can go to the field calculator, open field calculator. So I can create an output. So it'll be in area square kilometer, and I need it in decimal, and then I'll calculate area here as well. So it'll be area. Okay, so I need it in square kilometer as well. So I'm converting from square meters to square kilometers, so that's why I'm dividing it by 10 to the power 6. And then, okay, so now the total area of the whole catchment is this. So what I'm doing here is I'll just copy this number, Control C. Okay, so what I'm trying to do here is I just want to determine how much area this polygon has of the total catchment. Similarly, how much area this polygon has. So different polygons coverage, I just want to see the coverage. So what I can do is I'll create a different field here again. Open field calculator, I'll create a different field. So I'll name it percentage, or percentage of total catchment would be the name. It'll also be in decimal. So what I can do now here is okay, so I have area square kilometer, right? So area square kilometer divide by the number I just copied. So this is the area of the total square kilometer. This area square kilometers has stored the areas of each polygon. And then what I can do is, since I wanted it in percentage, into 100. Okay, it makes sense. Okay, so here you can see, so I'll show labels as well, not this one. I'll create a different so this is the catchment. So I'll open the attribute table as well. So what it means is, for example, my catchment number 10, right? So this catchment number 10 square kilometer is 2.055. I know the total area of the whole catchment. It's 27 point something something something, and that means that is the 7.548% of the total catchment area. And then again, if I look at this one, okay, so if I look at this percentage, so this is almost 20% of the total catchment. So in this 20%, I can apply, so let me on this as well. So in this 20% of the whole catchment, I can apply the rainfall values of rainfall station 4. So that is the meaning of it. So this Thiessen polygon is also one of the kind of neighborhood analysis, proximity analysis, which we can do in QGIS. This is mostly done when we have to determine, when we are dealing with hydrological data, rainfall station data and all. So thank you so much for looking at this video. I hope the concepts are cleared from this video. Thank you.